Hello class. Hope everyone's doing okay. Good. So we're going to start our last topic today before the semester ends. So today is lecture number 28. We're in chapter 15, pages 391 to 407 is what we're going to cover today. I think I mentioned the last class before the exam that you should read this, but if you haven't, you can pause the video and go read it now, or read it later. For next class, please 408 to 413. Homework. I have not decided on it yet while recording this, but by the time I send the email saying that this is done, I will have assigned you a homework. And actually, I know it's going to be when it's going to be due. It'll be due this coming Wednesday, right? Okay. No, today's or tomorrow when I upload this will be Friday, so it'll be due Friday. Okay. So today we're going to start this simple harmonic oscillator. And we're going to talk about the energy of this simple harmonic oscillator. So today we're going to start harmonic motion, also known as oscillations. And so this kind of concept relates not just to things you typically think of being an oscillation or a harmonic, like a pendulum swinging or a spring, a mass on a spring. That's the example we're going to go through in the class. Or a clock or anything else you would typically think of being a periodic cycle. Actually, everything in the world, everything in nature is some form of a harmonic oscillator, not necessarily a simple harmonic oscillator, because that, of course, is the simplest case we can examine. But the fundamental of a harmonic oscillator is that we have a periodic interchange between potential and kinetic energy, right? So those are the only two broad categories of energy there are. And they have the fundamental difference that one's related to motion, the other to the arrangement of particles. So anytime you have a force around and a system is capable of transferring via the force, a system is capable of transferring energy from potential to kinetic or kinetic to potential, you're going to see that the cyclic behavior arises, right? So anything in the world can be thought of as a harmonic oscillator because in some sense we always have some sort of interchange between potential and kinetic energy, right? Now, of course, we don't see every process just going through cycles and cycles and cycles. That's because these forces can be damped with other forces, right? If you think of a pendulum swinging, right? The pendulum will swing forever unless there's air resistance, in which case it'll eventually settle down, right? So even though we have a lot of harmonic cycles in nature, they don't continue forever typically. They get damped out. They also get driven and get bigger. And so there's lots of complications to talk about. But the fundamental of almost any physical process is some sort of harmonic interchange between kinetic and potential energy. Anything can be sort of seen that way. So this is not just going to be learning about springs and pendulums and rubber bands and everything else you can think of that would be an easy harmonic object, right? It's about broadly sort of understanding how energy moves around in the system. Okay. So, of course, we've been talking about springs in this class, right? It's one of the forces that we know how to use. We use Hooke's law, but we haven't really done any problems, you might have noticed, where we talk about what happens once that object has moved past the point of equilibrium and the direction of the force switches, right? Whenever we do problems, we say, okay, we up until now, we say we release the mass on the spring and it moves at this velocity, but we always stop before it gets, too far, so it goes beyond the point of equilibrium, right? Because then we have to consider more formalized dynamics than we've done so far. So today we'll do that. Okay. So as I said, the system we're going to start off studying is going to be a mass on a spring, right? This mass has some mass m. We're going to say there's no friction, no air resistance, no anything like that, and it's anchored to some point, and we have the equilibrium position somewhere, right? We define that to be x equals 0. So we know by Hooke's law that the force exerted by this spring on the mass is equal to negative kx, right? If we displace this mass in the positive direction from equilibrium, right, we put a positive number in here, the force in total is negative, so the spring is pulling it back this way. If we push this spring past equilibrium and compress it, right, this is a negative in the x direction compared to the equilibrium point. So we put a negative number in here, we get a positive force pointing in the opposite direction, right? So depending on which side of this point of equilibrium we are, this oscillation is going to continue back and forth, right? That force will point in one of those two directions. So to start to think about this, a good way is to first look at the graph of the potential energy of this system. So we know from our study of work and energy that whenever we have a varying potential energy, we also have a force, right? The first derivative with respect to position of the potential energy gives us a force, right? If we have some sort of force diagram, any slope in that force creates if we have a potential energy diagram, any slope in that potential energy creates a force pointing in a negative direction of that slope, which is just what we have here. So we can invert this and take the integral. So u as a function of x equals negative integral dx f of x. And we plug in our Hooke's law to get a potential energy for a spring. We get negative integral dx negative kx. And then this is k integral dx x, which of course is just k x squared over 2 plus some constant, which we're just going to set to 0. Okay. So let's graph this. And of course, it's a parabola, right? So we can think of these potential energy diagrams as like a little man climbing a mountain, or like a rolling ball sloshing back and forth. So imagine that if we put some sort of rolling ball on this potential energy diagram, this ball is just going to roll back and forth between these two rims or sides of this potential energy diagram. So it's going to fall down this way, and at this point, everything's going to be kinetic energy. We have no potential energy. And then as we roll back or move up the other side, right, that energy gets slowly turned back and back and back into potential energy, right, until we reach the energy of the oscillator to begin with, right? So we have this energy going back and forth and interchanging between potential energy and kinetic energy. Okay? So here would be like we have the spring compressed in the x direction, right? And then when we let it go, that mass zooms out, goes past the point of equilibrium, right? And at point of equilibrium, we have everything kinetic, that thing's moving the fastest. And then as it moves past the point of equilibrium, we have the force pulling it in the opposite direction, right? And then eventually that force overcomes that kinetic energy of the mass, and then it goes back and forth, back and forth, back and forth. Okay. So again, we have Hooke's law and Newton's seconds. We want to use these to find the dynamics of the system. We want to know the position of that mass as a function of time, right? And then we can get the velocity and whatever else we want. We'll know everything essentially. Okay. So we're just going to plug these two, well, rather set them equal. We get ma equals negative kx, and we also know that a is the second derivative of the position. So then we can just combine these two equations, and we get mass d squared x dt squared equals negative kx. Okay. So what we want out of this is the position as a function of time. So if I just wrote this down and I say, okay, find the position, you would start by trying to isolate the x. So to get x isolated by itself on one side, and then this equals to some other variables or constants that tell you how the mass moves around, right? But if you try to do that, you would find that you can't really isolate the x, right? Every term in the equation has something to do with x, and one of them is this differential, this second order differential with respect to position. Okay. So what this is called, this guy here, is a differential equation. Okay. So you'll get a whole class at some point, I'm pretty sure, on solving these kinds of equations. So it's sort of a non-trivial process, but this is one of the absolute easiest to solve, right? This is what you would get maybe on your first day of differential equations class. So you're going to get the little first taste of that now, and hopefully when you eventually get to that class, you'll think back fondly on this lecture and say, oh, I'm so glad Professor Click took the time to teach us this cool stuff. I'm so grateful for him. That's what I'm sure all of my students think. So we want to solve this equation. Okay, so let's be super lazy and try and solve it the easiest way possible. And the easiest way possible to solve it is to use what's called the guess and test technique, right? And it's literally like it sounds. You guess some solution to this equation and you test to see if it's right. So what we'll do is we'll make a guess for this x, right? We'll guess some function, and we're going to guess the correct function because I already know what it is, obviously. And then we'll check to see if that guess is correct, okay? Which indeed it will be, not to spoil the surprise. Okay. So if we were live, I would ask you to guess a solution for me to test, and I would prompt you by saying, think about how periodic systems move. What kind of function does that look like in time? And you would think about it, and then maybe some smart students would come up with, it should be a sine or a cosine, and I would say, yes, very good, it's a cosine, that's what we're going to try. So we're going to guess x is a function of t equal to a cosine omega t plus delta. This funny looking thing is a delta, a lowercase delta. Okay. So this isn't just a cosine, obviously. There's lots of other constants stuck in here, and those constants that I've stuck in make this equation the most general version of a cosine I can get. Right? Anywhere I could possibly put in a constant other than putting in an exponent, I put in a constant. Right? So let's talk about what these constants actually mean in terms of the cosine function itself. So if I'm going to draw a cosine function, I've got something that looks like this. Right? So this is time. This is x as a function of time. And the first thing we're going to look at is going to be that a that sits out in front of the cosine, that's the amplitude. Right? How far up in x does this function go when it's at its peak or at its trough, right? Some distance a up, right? Cosine itself, by itself, is bound between 1 and -1. So if we want that to be higher or lower, we need this amplitude out front. We talked a little bit about that when we introduced these functions. Okay. The next bit is this omega here. That's a lowercase omega. And that is the frequency, right? How often in time do I see one of these peaks go by or one of these troughs go by? How many times per second does a peak pass? Okay, how frequent are peaks or troughs in time? Okay, and that's just this distance between them, of course. And then the last bit is, is this delta, and that's what's called the phase. Right? So phase, amplitude, I'm sure you've seen before, and then frequency. Probably you've seen frequency before. So phase is how far this whole picture is shifted in time with respect to where that function would normally start, right? If it normally starts, a cosine 1 at t equal to 0, well, we don't have 1 at t equals to 0 here because this other constant we've added to that shifts it forward, okay? So we need to add on an extra amount of space, right? And by the way, a cosine function with a pi over 2 phase, with a 90-degree phase, is a sine function and vice versa. Okay? Sines and cosines only differ by a phase. And a lot of times we can just choose the phase to be whatever we want because that's just a choice of coordinate system, right? I could just define this point here to be x equals 0 and then the phase would go away. Phases are usually only important when we're talking about more than one wave, when we need to compare two different waves in time, okay? But we won't do that in this class. Oh, this will come up a couple times. Okay, so now it's time to test our guess. So this is going to be a little tricky because actually these are the largest equations as written on the board that you'll see in this class. So I'll have to be careful to try and squeeze them in. So I'm just taking that function, the a cosine omega t plus delta, and I'm plugging it in that differential equation that I wrote 2 boards ago, right? The second derivative of x with respect to time times the mass equal to negative kx, okay? So first we want the second derivative of x with respect to time. So I'll write and then I'll talk when I'm done writing. Okay, so this will give us that first bit that we need. Excuse me. I'm sorry. Give me 1 minute. Okay, I'm back. Okay, so we take this derivative. So remember the chain rule. Right? So we take first derivative, and then we do derivative of the outside, that gives us a negative sign. And then we do the derivative of the inside, which gives us an omega. Okay? And then we do the second derivative, and then we get a omega squared cosine omega t plus delta. Okay. So now we have x, we have the second derivative of x, so let's plug that into our equation. So I'll write it in full again. Okay. So now we have and this is the same thing in here that is in there. I just ran out of space. And now, the nice thing about using sines and cosines in differential equations is that, if you take that the derivative of that trigonometric function twice, you get the same trigonometric function back times a constant, right? Which means that if I have that function on either side of the equation, I could just cancel them out. And then we're just left with from omega squared equals k. So we have essentially a condition on our test being, or on our guess being correct, right? We guessed that function a cosine omega t plus delta, and this tells us that as long as this equation is true, this guess for that equation, the original equation, x as a function of t, is correct. Okay, so we found the answer essentially. And if we invert this, we see omega equals the square root of k over m. So we have an equation that tells us what the frequency of that oscillation is, and it's the square root of the spring constant over the mass, right? If we have a very stiff spring, right, a really high spring constant, well then our frequency is going to be really high. We're going to have really fast oscillations, okay? If the mass is really high, right, then that oscillation is going to be slower because the force is going to take more time to act on that larger mass, right, to get it to change direction, essentially. Okay. And one really nice thing that this demonstrates is that these simple harmonic oscillators make excellent clocks because the frequency, the regularity that it beats out a time, right, that a trough passes or a peak passes, is given by the spring constant over m and nothing else. So it doesn't depend on time itself or anything else. I can use something that obeys this type of harmonic oscillator equation, like a mass on a spring or a pendulum. The pendulum is only when the angle is very small. Otherwise, it's more complicated. I can use something like that as a clock. Okay. So if we wanted to, then we could write out our full solution, right? X as a function of time is equal to a cosine square root k over m t plus delta. Okay. But we still don't know amplitude or phase. So, amplitude and phase are pretty easy, right? And we find those by examining the initial conditions of the system, right? When we look at the system as it's just starting out, right, how displaced is it from equilibrium when we press go on our stopwatch? Okay, that gives us our phase. Now, we can always, of course, move that that origin in time. We can choose when we press go on our stop clock, and so we can eliminate the phase. So we can just set that to 0. As for the amplitude, this is just the x position at the initial time when we start our clock, right? If this phase is in fact 0. Okay. Okay. So that should be pretty straightforward. And now, the next thing is I want to talk a little bit, actually, before I talk about the energy, I want to be clear about a couple tricky points. One is that there are different definitions of frequency, right? This is the first time that well, maybe it's been important before, but it's especially important now to make a couple distinctions. One type of frequency is angular frequency, and that is written omega and use units radians per second. And then what we call regular frequency, or what I call regular frequency, right, in terms of cycles per second. So you can have radians per second, the angular frequency, or we can have what's usually just called frequency, the number of cycles per second. And this is usually written with a script F and has units hertz, right, which which is cycles a second. And if we want to convert between them, we just have to multiply by 2 pi. And if we're talking about periods, right, the inverse of the period is the frequency, the regular frequency. So it's many a student has lost 1 or 2 points because they forgot to multiply by 2 pi or had an extra 2 pi. Okay. Just a word of caution. Okay. So we know that potential energy. Now let's talk about energy. So we know that potential energy is 1/2 k x squared from when we, that second board or first board. And we just have to plug in this function, which gives us 1/2 k a cosine squared, and stuff goes in there. And then for kinetic energy, we have 1/2 mv squared. Okay, so we need the velocity now. Right? We can get the velocity by taking the first derivative of the position. So that velocity equals dx dt, and I'll just write it like this. That kinetic energy in total is 1/2. So after a line or two of algebra, so now, let's look at the total energy. The kinetic plus the potential energy. So we have 1/2 k, well, that should be an a squared. Squared plus sine squared plus sine squared. Okay. And then this, of course, is 1, because cosine squared plus sine squared is 1. So we have the energy total of this system is 1/2 ka squared. So what this means is that the energy isn't leaking out anywhere, right? The spring force is a conservative force. So no energy is leaving the system. The energy stays constant as a function of time, and it's given by 1/2 ka squared, right? And it's easy to see why the energy should be related to these two things, right? The stiffer the spring is, right, the more energy it takes to compress or stretch it. So the more energy we store in the system initially, right? The amplitude, likewise, the more that we stretch it or compress it, the more energy we put in there, right? So those two things together tell us the total energy, which is invariant in time, right? Because this cosine plus sine squared, which is the only place we have the time, right? Time down here, right? That just ends up being 1. Okay. So actually that went really quick. It's only been half an hour, but that's all I wanted to get through in this lecture. And next lecture we will start talking about a damped harmonic oscillator, right? So now we're going to bring in some realism that spring is not just going to oscillate back and forth forever. There's going to be some air resistance or friction or something like that. So we'll analyze that case next class. Okay, hope everyone has a nice weekend.